Hello everyone. In this project, our objective was not only to minimize RMSE on Kaggle, but also to make sure our regressor is properly fitted in a generalized wheel. In this presentation, we will explain clearly what we did to improve performance and how we assessed and improved the model fit. We begin by loading and training and test datasets. We separate the test ID column because it will be used in the final submission file. This step ensured our full pipeline works from raw data to final Kaggle output. It established a functioning regressor system, which is the foundation of the assignment. The first major performance improvement step is outlier removal. We remove houses with very large living area but unusually low price. These observations do not follow economic logic. If we keep them, this distort regression coefficients and increase variance. After removing outliers, we apply log transformation to set price. Housing price are highly right-skewed. Log transformation stabilized the variance and makes relationships more linear. This directly improves the RMSE and helps linear models perform better. At this stage, we are already reducing both noise and the variance in the dataset. Next, we combine the training and test datasets before feature engineering. This ensures both datasets receive identical transformations. If we process them separately, we risk inconsistent encoding or missing features. Combining them avoids data leakage while maintaining consistency. We then analyze numerical feature skewness. If a feature is highly skewed, we apply log transformation. Skew inputs can cause unstable model confidence, especially in the regularized regression models like the lasso or elastic net. By correcting skewness, we improve linearity and reduce extreme influence. This lowers model invariance and improves predictive stability. Feature engineering is the most important performance improvement step. First, we create a neighborhood median price feature. Locations generally affects housing value. This feature captures local pricing structure. Second, we create a total SF by combining basement and the floor areas. Instead of forcing the model to learn the relationship separately, we provide a direct measure of total size. Second, uh, third, we create an interaction between overall quality and the total square footage. Economically, size and quality together determine price more than individually. This interaction captures that nonlinear effect. Fourth, we create a feature multiplying year built and total square footage. Newer, larger houses typically command higher prices. This reflects market logic. These engineered features reduce bias because they encode domain knowledge into the model. We apply one-hot encoding to convert calorical variables into the numerical form. We remove columns containing only zeros to reduce the dimensional noise. Then we fill missing values using median. These steps improve model stability and reduce unnecessary complexity. Before modeling, we apply the robust scalar. Unlike the standard scaling, it is less sensitive to extreme values. Since we are using linear models, use regularization, proper scaling improves convergence and reduces instability. To further improve the performance, we use multiple base models instead of relying on one. Lasso and the elastic net provide regularizations and the feature selection. Kuber regression is robust to remaining outliers. XGBoost captures nonlinear relationships and complex interactions. Each model has different variance characteristics. Linear models have higher bias but lower variance. XGBoost has lower bias but higher variance. By stacking them, we combine their strengths. Write CV as the meta-linear lens option on optimal weights across models. This reduces both bias and variance and improves the generalization. This ensemble strategy is a key reason for improved Kaggle performance. To assess model fit, we deploy a learning curve using the cross-validation. The learning curve shows the train RMSE and the validation RMSE at different training sizes. We observe that as training size increases, validation error decreases and the gap between training and the validation error narrows. This indicates the model is not strongly overfitting. If the gap was large, that would signal high variance. If both errors were high, that would signal high bias. Instead, we see convergence behavior, which suggests good generalization. This directly satisfies the rubric requirement of proper extending model fit. After the validating model fit, we train the final stacking model on the full dataset. We also train the elastic net separately and blend the predictions. We use 75% stacking and 25% elastic net. Stacking provides strong predictive power. Elastic net provides stability and reduces bias. Blending balances bias and variance and slightly improve final RMSE. To summarize, we improve the performance by removing outliers, applying log transformations, engineering economic, meaningful features, combining multiple models, using stacking and applying blending. We assist and improve the fitting by using cross-validation, analyzing bias, variance, trade-off, and deploying a learning curve to evaluate convergence. This ensures the model is not only accurate but also well fitted and generalizable. Thank you.